All right, so today we're going to talk about end behavior models. So the basic idea with an end behavior model is that you can take a fairly complicated function and replace it on the far left or the far right with a simpler function that does the same thing. Okay, so how do we define that? Well, the function g is a right end behavior model for f if and only if the limit as x goes to infinity of f of x over g of x is equal to 1. So that they're doing basically the same thing. It may not be exactly 1 the whole way, but as x gets really big, these two are doing the same thing. Likewise, a left end behavior model if and only if the limit as x goes to negative infinity of f of x over g of x is equal to 1. By the way, since those are 1, we can also do g of x over f of x. It really doesn't make any difference. Okay? So, for example, and that should say an end behavior model for f of x, not and end behavior model. Let's see if I can fix that. That's not... There we go. It's not very good, though. It's not wide enough. Probably. I bet that's what's going on, is the opacity is not... That's why the blue isn't as dark as I want it to be either.
I wonder if there's like a preference.
There are. I'll have to fix them later. So an end behavior model for this really hideously long polynomial is just... Pardon?
It's quadratic equation.
It's not a quadratic.
I know, I just said that.
It's a quartic.
Well,
Yeah, your
is there a
quartic
quartic equation?
No. Nor is there a quintic.
Triplet?
Is g of x is equal to 3x to the fourth. Verify this analytically and graphically.
I love graphics.
All right. So to verify this analytically, we want to take the limit as x goes to infinity of, I'm going to put the ugly one on top. What's rude about that?
What?
I didn't say I was going to put your mama on top. I mean,
This is why I had so many subscribers from YouTube.
so this will then be the limit as x goes to infinity. And I'm just going to do the division. 3x to the fourth over 3x to the fourth is? 1. Minus, this is going to be 2 over 3x. Plus 1 over x squared. Minus 5 over x cubed. Plus 2 over x to the fourth.
Bigger.
What happens to all of the terms except for the first one as x goes to infinity?
They get bigger. Smaller.
Really?
You get small.
They get smaller, close to 0, correct?
Yes.
So this is 1.
Well,
Likewise, the limit as x goes to infinity or negative infinity of f of x over g of x, that's going to be, well, exactly the same thing, isn't it? So we have analytically verified that that is an end behavior model. Now, let's verify that graphically. So I'm going to grab my calculator and go, okay. Got to wake mine up. Get rid of this junk. Type in the first one, 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6. And the other one is 3x to the fourth. And I'm going to do a zoom standard just to start. And you're like, okay, that's kind of hard to see that there's anything going on. I would look at the table. And mine's already, because I had it set from the other day when we were playing around with stuff. At, by the time you get to 2,100 to 4 decimal places, they're exactly the same. And you can see that those are pretty big numbers. 1.6 times 10 to the 14th at 2,700. That's a big number, but it's the same big number, right? So we've showed that they are doing the same thing graphically. All right. So for polynomial functions, the end behavior model is simply the polynomial's leading term. Remember, the leading term is the term that has the highest power on x. Okay, it may or may not be the first term. So if I'm looking for an end behavior model for these rational functions, what I'm going to do is go, okay, I'm going to start, let's do a different color. I'm going to start by taking the end behavior model for the numerator and the end behavior model for the denominator. So here that's going to be 4x cubed over 6x cubed. Well, that's going to be 4 over 6 is 2/3. So y equals 2/3 is the end behavior model for that. That's it?
Excuse me, Mr. Davis.
Yes, ma'am.
You don't have second grade, correct?
I do not.
Okay. I need a cover for Kelly, because she's at the doctor with Julia for an x-ray.
Uh-oh.
Yeah, she hurt her ankle in a tournament over the weekend.
Oh, gosh.
Yeah, so I just wanted to make sure. So that's where I'm going now.
Okay, cool. I'll leave the door unlocked.
Okay, great. Thank you.
Thank you. Appreciate you being here today. All right, so for this one, let's see. The end behavior model for the numerator is 3x to the 5th. The end behavior model for the denominator is 6x squared. So the end behavior model for this is 1/2 x to the 3rd.
If you want to make our quiz just like this, you know, you are going to be gone probably, so, you know, call it time
All right, so now let's take a look at this one. Find a left and right end behavior model using a calculator for f of x equals x plus e to the negative x.
I'm hurt.
All right, so let's go back to y equals and let's clear these things out. And let's take a look at what x plus e to the negative x.
Does it matter lens when you have my movement?
Yeah, it does. You move that.
And I'm going to do something that I will occasionally do. Do you know that this is a distorted graph?
It's not big enough.
Why is it how is it distorted?
Your screen can't display it all.
That's not it. That's not the distortion.
The axes aren't equal.
Yeah, the spacing is not the same. This goes from negative 10 on the y-axis to negative 10 on the negative 10 to positive 10 on the y-axis, and negative 10 to positive 10 on the x-axis, but your screen is wider than it is tall. This is not what this actually looks like quite. So once I have that, I get it in a window that I like, and then I do zoom 5, which is zoom square.
That's definitely
It's Bank of America now.
not my
Oh, it's
That is a better picture. All right, so over here on this side, what does that look like? Just generally speaking.
Straight line.
Yeah. Mm,
Is that your general?
may go for his jugular next time he says that. Yes.
Looks like a line.
All lines are straight. So
It's curved.
it's curved down here, but it looks fairly straight up here, right?
But would a curved
So
line-
what is the linear part of this?
The X.
The x. So let's test that. If I check this against y equals x on the right side, and so I can see it, I'm going to make this one
Oh, wow.
bold.
How do you make it bold?
Move all the way over to the left and hit enter once.
Yours is in color.
Mine's already
Oh, yours is in color? Yeah, the color ones I actually like that.
Well, I have different line options too.
So look at that.
Face the background of the ground. Whoa. That is pretty cool.
Hey, Mr. Davis.
And
After
you have a red.
class,
That's
do
great.
you think I can take a picture of you so I can put it as my graphic in the background?
No.
Please?
All right. So did you see that these look practically identical?
Yes.
So the right end behavior model is y equals x. So I wonder what the left one might be. Do you think it might be e to the negative x?
Whoa. I didn't know.
Let's see if it is. It might not be. So e to the negative x, second e to the negative x. So there's the original. It's pretty close over here, isn't it? Let's go back to the table. I like that I've got my table at such large values. You know, like, something's not right there. Oh, I'm at really big values. I need to go the other way. It's like, wait a minute. La-da-dee, da-da-dum, da-da-dum-dum-dum-dum-dum. It starts giving you error. Why the heck is it giving me error?
It gets small.
Actually, the other way around.
It's big.
It got so big. If you go back to negative 200, it's 7.2 times e to the 86th
Yo, it can't go bigger than that?
No.
times 10 to the 86th. I think it craps out at 10 to the 100.
That's pretty big.
Yeah, that's pretty big. Okay, so the right end behavior model, or excuse me, the left end behavior model is y is equal to e to the negative x. And that's because e to the x is an incredibly fast-growing function. So the fact that you're adding x onto it, it doesn't make much difference. Okay? All right. Moving on. Every now and then, when you're trying to find the limit as x goes to positive and negative infinity, it's easier to find the limit as x goes to 0 of f of 1 over x. Okay? Take this example. If we just kind of try and substitute into it, well, as x goes to infinity, that goes to infinity. And 1 over something infinite is going to go to 0. And sine of 0 is? Nope. Got to know that, guys. Sine of 0 is 0. That needs to be as automatic as breathing. Sine of 0 is 0. Cosine of 0 is 1. E to the 0 is 1. Natural log of 1 is 0. Those have to be like breathing in and breathing out. Okay? And here we have a problem. Because this is not equal to 0, it's a really small number near 0. And this is becoming really big. When you multiply those together, what do we get?
0. I don't know.
It's not, but it's not equal to 0. It's really small.
Indeterminate.
It is indeterminate. This is actually one of the indeterminate forms. So how can I handle this? Well, what I can do is rewrite this as the limit as x goes to 0 of, replace all the x's with 1 over x's. So this would be 1 over x times sine of 1 over x. What is 1 over x?
That would be
X.
X. So that's the limit as x goes to 0 of 1 over x times sine of x, which you might recognize better if you rewrite it as the limit as x goes to 0 of sine of x over x. It's equal to 1. Very good.
Good job, everyone.
Thank you, Lance.
That's because you're Python calculator.
That's okay. Listen, I've noticed that my calculator can do its graphs faster.
Yes, the new Python one is faster than the old ones.
Yes, and even like Lance's
Wait, let's
normal
hear it.
84C.
What's different about yours than mine? It's got Python on it.
Yeah, they had to make the chip beefier
Does the inside Python?
enough to handle Python. But it's not like I'm going to use Python on here. I got this because it was $50 off.
Nice.
I thought you got this because your mother got it.
Yeah, yeah.
So your mother got it because it was $50 off.
Yes.
So
Not
made it 105, which is the same cost of a normal CD.
all right.
Because you didn't show up with the TV.
Any questions about that?
That's dumb.
If you want to make this page our quiz, that'd be